Okay, well, welcome to our first chapter summary video for Module 1. This is going to take the place of our usual class lectures. In principle, you could use this in lieu of the readings, but I really do want you to do the readings also because I can't cover everything in the text, obviously, in a lecture. So I want to start off talking a little bit about what statistics is. And by the way, if you didn't see it, I have a copy of these notes on Canvas right next to the video. You may want to print those out and download those because my handwriting is not that great. It's one thing that students complain about, and I totally empathize with them. So I give you kind of a shell of the notes. That way, you know, you don't have to try to decipher my reading quite as much. So I'm going to just ask you kind of an open-ended question now. This is going to be part of the reading quiz. I want you to answer what you think statistics is. Okay, so what statistics actually is, we're going to say that it's a rational process and if you want to, you could replace science by rational process. In other words, it's some methodology that has a rational basis, right? Not like astrology where, you know, people say it works and if you ask why, they can't tell you. In this case, there actually is a reason why statistics works, and it's probability theory. And we're going to get into that as the class goes on. So we could say that it's a science that we use to make decisions from data. So this is what statistics is. Very different than probably what you would have thought statistics was before this class started, right? All right, what is data? And so this is a little bit circular, kind of in a dictionary. You look up one word and it tells you to look up another. But data is one of those things that people really don't understand that much. So data is any collection of recorded observations with context. And context is so important, I'll be very dramatic and I'll put it in red marker. Okay. And we talked a little bit about what context was in the introductory video, right? We said that context is really the background information we need to make sense of the data. And when we say make sense of, okay, we mean, first of all, we want to understand what is it we're looking at. When you look at a spreadsheet, it's just numbers. And sometimes people will have headings in each column telling you what the variable is. But sometimes the variable descriptions are very short and they aren't necessarily obvious what it is you're looking at. So first we want to understand what are the data values we're looking at? What do they represent? What are their units? But we also want to understand more. We really want to understand, in a sense, the pedigree of the data. Where does the data come from? And we're going to get into why that is such an important issue. But you can kind of see from these three statements here why that would be the case, okay? We're going to be making decisions, and The decisions we're going to be making are about a population. And we're going to be getting the data from a sample. Okay, so if we have bad data, like that, that hypothetical I gave you with the Embry-Riddle professors, right? If you have a bad sample, a sample that's not representative of the population, you're going to make very bad generalizations and decisions about the population. So that's kind of the basic idea, okay? So what I want to do now is talk about this first step in the process of statistics that Triola calls planning. So he says that statistics has 3 phases: planning, analysis, and conclusions. And that's actually a very nice, succinct way of summarizing that process. So if you go to the second page of your notes now, I call this anatomy of a statistical study. In other words, this is the planning phase, okay? And the reason why this is such an important aspect of statistics is people generally have this notion that statistics is formulas and calculations. And no doubt that plays a role in statistics. You can't have statistics without them. But the really important part of statistics, the crucial part, the part where studies go wrong, is in this planning stage. And that's the important thing to understand, is that statistics is not mathematics. It's much more like a science. And one of the analogies we're going to use throughout this class is we're going to think about statistics as kind of like a murder investigation. Kind of like CSI. We're going to be gathering clues and facts and putting things together and using logic and stuff like that. And that's really what statistics is much, much, much more like. Okay, so some people would say, and I would be among them, that planning is really the most important stage. Of all of these 3 phases. Even though analysis, which is where the calculations and formulas and graphs and everything come in, is important, the calculators do all of that for us. We're going to use Excel. We're rarely going to actually ever have to calculate anything by hand. In fact, I think I can say with a high degree of certainty, we'll never compute anything by hand. So all of this stuff is already in the computers. We don't have to worry about it. The place where you mess up is in the planning. And the reality is that if you have a poorly planned study, you can't do anything with it. It's worthless. So, I had mentioned in that one video about how I was doing that consulting job with the mathematician and the statistician. And that was the whole point of the story. The statistician recognized that if you have bad data, no matter how good you are mathematically, you can't do anything with it. It's useless. You have to throw it out, okay? So planning and the preparation stage really has to do with how we're going to collect the data. And so what I want to do is I want to try to illustrate what's going on in this step by giving you an example. Okay. So the example that I give in the notes is an example about the COVID-19 positive test rate in Florida. Before June 5th, the positive test rate, in other words, the percentage of people who were tested for COVID-19 and had a positive test, was around 4.2%. It was a little north of 4%. On January 5th, Governor DeSantis gave orders for the state to begin phase 2 of the state's reopening, which involved bars and restaurants and things of that nature beginning to open up. And you could ask the question, well, did the COVID-19 infection rate go up? Well, if you live in Florida or you watch the news, you know the answer to that is yes. But how would we plan a study? Okay, rather than just believe somebody, how would we do it ourselves? So here's what I want to impress upon you. When we start a study, we start off thinking about the population. The population, if we kind of think about context here, okay? We think of the population as some large group of individuals that we're interested in. So we're going to think of the who we're interested in studying, as the population. And this is going to be the collection of all things we're interested in. It can be people, but if you're running, say, a manufacturing line at Boeing, it could be hinges, or it could be screws, or anything, right? Just a collection of things we're interested in. But it's all the things. So it's okay. And the book calls, and it's very common to call things units, or experimental units. Okay, I'm not going to use that term, but you'll hear that term a lot, especially if you read the book. All right. So in this case, who is the population? Who are all the people we are interested in knowing about? Well, it's everyone in the state of Florida, right? In other words, if you were an omniscient being, what is the largest collection? All of the things that you're interested in having this information about. Well, I'm interested in the infection rate of Florida, so I want to know what percentage of everybody in Florida, if I tested them, would come out positive, right? Okay, the next thing we have to understand is this thing that we're going to call the variable. This is what we're collecting data on. The book doesn't talk about variables. I think that's an omission on their part. The use of the word variable is really important in statistics, so I am going to use it on a regular basis. We think of a variable as anything that we can measure from every single person in our population, and the value cannot be known before we take the measurement. So we think of it as something we can measure. The values vary among the people in the population, but we can't know the value of that variable for any one individual until we take the measurement. So suppose you're talking about heights, okay? And I'm recording the heights of people as they come around a corner. Okay. Height is something I can measure. Height varies from person to person. It is a variable. And sometimes people use the word random variable, because I can't know each person's height until they actually come around the corner and I measure them. That's the idea of a variable. And it's the thing I'm going to be collecting data on, right? The why, and this is the tricky part. And I'm going to put this in red because this is an extremely important term. So we talk about the parameter for a variable, or a parameter of a variable. And here's what a parameter is. If you could know the value of this variable for everyone in Florida, okay? So the way a statistician thinks about it is he thinks of people as like little balls in a bag, okay? And they have the value of the variable in them. So this is the person that would test positive, they have a yes. Person who would test negative, a no, right? And I mean, I don't have all day to spend doing this, right? But I'm going to fill in a few here. But this population is huge, right? I mean, the population of Florida, I don't remember it right offhand. So we had this huge population, right? And, dot, right? If I could know for every single person whether or not they would test positive, what is the one number I would want to compute from all of those yeses and nos? That's what the parameter is. It's the one number you would compute if you had the value of all the variables in the entire population. So the parameter comes from the population. And what it is it is the one number you'd compute if you had the values of all the values of the variable from everyone in the population. So if I had all of these yeses and nos, what's the one thing I would want to compute from all of these values from everyone in the population? I would want to compute the percentage of people who had yes. And that's the idea behind a parameter. We're going to talk about this a lot more. Okay. Last thing we want to focus on is how. How are we collecting this data? So first of all, there's two issues, right? Sampling comes into play, how we take our sample. And we're going to talk a little bit more about that later on. Notice that in that introductory example, right, the sample was not taken well. That was not a random sample. This is the idea. We want a sample where everyone has the same chance of being chosen. So we sometimes call this a random sample. So the idea here is that we want the sample to be random, and we want it to be large enough. These are the two main issues with sampling. We don't want a biased sample. We want a sample that looks like the population. So again, kind of going back to this, ping pong ball sort of analogy, a statistician imagines mixing everyone up, okay, and then choosing each individual randomly, just reaching in a bag, closing his eyes, and picking someone. How you do that in real life, it's a little trickier than that because people aren't ping pong balls, right? So that's a bit of an issue. But there are ways of doing it. And again, our sample has to be large enough. Too small, we can't make generalizations about the whole population, right? There's also a question, though, as to how we make our measurements. And we're not going to get into this issue a lot, but this has to do with how are we actually measuring the variable? So for example, if you're asking people how tall they are, that's called self-reported. That's not good. People tend to say they're a little taller than what they are, right? People ask me how tall I am. I say 5'9". I'm probably not quite 5'9", okay? People do this, right? So if our measurements are self-reported, they're not going to be as reliable. All right. So these are things that we have to think about when we're making measurements. And of course, what happens in a statistical study? Well, generally, we can't get everyone in the population, especially when you're dealing with people, right? Populations are too large, it's too expensive, too time-consuming. Not everybody wants to be in a study, right? Some people don't want to be found, okay? So, and you can't get information from them. So what do? Well, we take a sample, right? So I kind of reach into that bag randomly, and I take a sample. A snippet, a portion, a chunk. Think of a sample in a statistical study the same way you'd sample soup, right? You mix all the ingredients up, you take a spoon, and what is on the spoon should look like what's inside the sample, and what's inside the pot, right? And the idea is from this sample, I'm going to estimate this parameter I'm interested in. Notice this whole study is being done to try to figure out what the percentage in the entire population is. I can't get that. So what's the common sense thing to do? It's to estimate it from the sample, right? If the sample really looks like the population, okay, if it really is representative, if the composition is the same, then the estimate I compute from the sample should be close to the population parameter. So in this case, right, I have, let me put in a few more so that it's a little more representative of Florida, okay? I want a few more no's in there. And this sample would be nowhere near big enough to use in real life, but I'm just going to do this, right? So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. So in my sample, I have one person that tests positive, right? And 9 that test negative. 1, 2, 3, 4, 5, 6. Those are actually n's, 7, 8, and 9. So for my estimate, for my sample, I'm going to compute a statistic. This is an important term, parameter and statistic. Okay. Parameter is the value from the entire population. A statistic is anything we compute from a sample. Anything we compute from a sample. And generally, the things that we compute from the sample are the estimates of the parameters, right? I want to know this whole population percentage. I can't get it. So what am I going to do? I'm going to estimate it with the percentage from the sample, or the sample percentage. And that's normally the statistics that we're going to be interested in, okay? So the old joke is, they say, don't drink and drive and become a statistic. Well, you can't become a statistic, right? You can become a data point, but you can't become a statistic. So I know it's a bad statistician's joke. Okay, so now we have this under our belt. This is kind of the idea behind the planning. We want to know who are all the individuals we're interested in, what is it that we want from them, what do we want to do when we get the data from them, and how are we going to get the data to compute what we want. This is the logic of how the planning phase goes. And obviously, it's a lot more involved than that. If you read the book, you'll hear about, systematic, stratified, cluster sampling, multi-stage sampling. In real life, it's a lot more involved in that. But this gives you a basic idea of the principles, the sort of logic and what it is that's going on. So we want to now focus a little more on the variable. It turns out that not all variables are the same, and different types of variables are going to require different sorts of treatment. In particular, they're going to require that we analyze them different ways. And I don't know that I'll reproduce the entire table on page 3, but I'll hit the main points. So we're going to call this data the data type of a variable. So in the same way that parameter referred to a variable has a data type. And so one of the things you should realize is that different types of data, different types of variables have fundamentally different types of values. So if we go back to our COVID example we were just talking about a second ago, our variable was whether or not a person tested positive. The values for that variable were yes and no. Whoops. Don't know where the yes came from. All right. Yes and no. I cannot do mathematics with those raw data values. And that's important to recognize. So this is an example of what we call a categorical data type. Sometimes people just say categorical variable, and I'm going to say that myself, but if you want to be very proper, you would say that the variable is of a categorical data type. But I'm going to call it a categorical variable. And sometimes I'll abbreviate that by cat var, just because it's faster and everyone does it. And categorical variables are variables whose values represent different classes or categories. Okay? So they can represent different categories. Yes, no, male, female, right? Jewish, Hindu, Muslim, Christian, those are all different categories. There doesn't have to be just two, right? Okay. So this is the idea. But they can also represent different types of things, not necessarily categories per se. They can be identifiers. So for example, zip codes. You could think of them as categories, but you could also think of them as identifiers. Bank account numbers, social security numbers, student ID numbers. These are all data, right? But these are all identifiers. They're really identifying you. Sometimes they represent different levels. And what we mean by this is we're looking at a situation, and sometimes people also call these rankings, where we're ranking something. So, for example, all the time when you call companies, they'll have satisfaction surveys afterwards. How satisfied were you with your, customer representative? 5, if they were great. 4 if they were good. 3 if they were okay. 2 if they need some improvement. 1 if they suck. Something like that, right? And same sort of thing here. Now, something to realize is that they can be numbers, right? So very often rankings are numbers. Okay. These can be numbers. These are generally not numbers, but sometimes they're coded numerically. It's not uncommon to have a data set where males and females are coded numerically. So 0 is male and 1 would be female, right? Because females are greater than males. Everybody knows that. At least that's what my wife tells me. All right, so that's sort of coding. But does 0 and 1 mean anything? Of course not, right? They're just ways of coding. They're called binary codes, okay? So these can be numbers. But they don't have to be. Now, one of the things you should realize is that when a variable has values that are characters or letters or words, okay, it's automatically categorical. So if you're looking at a column of a data sheet and you see male, female, died, survived, maybe different denominations of religion, right? These are all words automatically categorical. If it's numerical, the way that you could tell it's categorical is the fact that 2 things will happen. First of all, if it's a number, it won't have units. This notion is really important. Sometimes when people look at rankings, they say, oh, it's not categorical because I'm measuring the amount of something. No, actually you're not, okay? Because you don't really have units on this, okay? You're measuring a sentiment, really. It doesn't have units. You also can't do meaningful math with the values. You have to be a little careful here. So what meaningful math means is that the differences of the raw data values make sense, averages make sense, and stuff like that. So if I take the average of your bank account number and my bank account number, does that mean anything? No. It gets a little trickier when you get to rankings, okay? But still, if I rank something a 5 and you rank it a 3, does that difference 2 mean anything? No, because it's so subjective, right? So it isn't really meaningful. I'm going to mention one thing very quickly, okay? So for those of you who know statistics well, you'll realize that this last category we're calling levels is actually a special type of data called ordinal. And these things are actually what we call categorical. And this is usually what people call qualitative variables, okay? I'm not going to use that nomenclature, and the book doesn't either, but you might have come across that, okay? So some people refer to this as qualitative. This is categorical, okay? These have categories. Identifiers are a category of 1. And this is called ordinal because the values have an order, right? 1, 2, 3, 4, 5, whatever, okay? The parameter for a categorical variable, and this is important, is always the population percentage. So I'm just going to write the word param. So the parameter for a categorical variable is always the population percentage. When we think about a categorical variable and we're doing analysis, we think of each category separately, and we think of that category and all of the others that are not that category. Okay, so if I'm thinking about, for example, like different types of religion, and I'm interested in what percentage of people are Hindu, I kind of dichotomize the population and think of Hindus and non-Hindus, even though that non-Hindu group comprises a lot of different categories. Okay, so on the other hand, we have variables that can take on numerical values. So for example, if we look at the heights of Embry-Riddle students, so I go out and I measure a bunch of students, right? I may have, one student that looks like 66 inches, one that's 70 inches, one that's 62 inches, etc. And these type of variables are called quantitative variables. And the reason why, just as their name suggests, they're measuring the quantity of something. Quantitative variables always fall into one of three categories. The majority of them correspond to physical measurements. So anything I can measure physically, height, weight, time, volume, pressure, speed, I can go on and on, right? This is always quantitative. The other is count data. And by the way, quantitative measurements that represent physical measurements are generally what we call continuous variables. In other words, their values are thought of as filling up a number line, okay? So if you think about people, for example, what's the smallest person? I don't know. I'm just going to make up a number. Say they were 3 feet tall. Okay, so we're going to say that people's heights can go from 36 inches, and who was the tallest person? I don't know, but let's say they're 8 foot, okay? Up to 96 inches. And in principle, a person can take any value in between there. Now you might say that's stupid because I can only measure height to a certain precision. And you're absolutely right. But that's not how we model height, okay? It's important to understand that. So when we're thinking about a quantitative variable, we're thinking about it in a kind of theoretical way that we can measure it to any level of accuracy, all right? And you might say that's not realistic, and you're absolutely right. But again, we're modeling height. The model doesn't have to be exact. All it has to be is useful. And it turns out that it's very useful for us to treat data that way. Okay, the other type of quantitative variable you can have is count data. In other words, I'm counting a number of things. Like, down here, right? I was counting the number of no's, 1, 2, 3, counting something. Number of students watching this video, number of job offers you'll get next summer, right? This is all count data. Count data is discrete. And I'm not going to get into a big explanation of what I mean by discrete, but basically, for our purposes, it means that it can be a counting number, okay? It doesn't have to have an upper bound, all right? Like the number of students watching this video is capped by the number of people in class, right? So that's called countable finite. We're not going to get into these fine terms, but it doesn't have to be. Like, for example, the number of errors the Chicago Cubs can make in one season, right? It could be anything. It could be 0, 1, 1,000, whatever, okay? Doesn't have to have an upper bound. The last one is the one that's the most missed by students, and that is percentages. Okay. So percent of the class watching this video, that's a quantitative variable. Now, what do all three of these things have in common? Suppose you get on an exam and you're looking at a question, you're like, I have no idea if this is quantitative or categorical. The key property of a quantitative variable is that it has units. That's the key thing. Okay. Physical measurements obviously have units. Count data has units. If I count 9 cars, each one is a unit of 1 car. Percentage has units. Percentage of the whole, okay? The other thing is that you can do, meaningful math with it, okay? I can take averages of physical measurements, right? I can take differences in counts that are meaningful. If you have 5 balls and I have 3 balls, and I take away, and we look at the difference between the number of balls I have and number of balls you have, that's 2. That 2 actually means something, right? That actually has a real, actual meaning. Whereas for categorical, that difference in the rankings doesn't actually mean anything. Okay, the parameter, well, it turns out quantitative variables are much more complex than categorical. The primary parameter we're going to look at, well, let's kind of puzzle through it. Okay, let's use the definition of the word parameter. Suppose I had all the heights. Suppose my population is all the Embry-Riddle students. My variable is height. I have the heights of all the Embry-Riddle students. What is the one number you think I would want to compute from all of those values? If I had the heights of all the Embry-Riddle students, what's the one number I'd want to compute? Well, if you said mean, you got it right. And this is, of course, the population mean. All right. So these are the data types: categorical, quantitative. These are the different ways in which categorical variables manifest. General properties they all share. For quantitative, these are the different ways that you can have quantitative variables and what the basic property, general property of all quantitative variables are, along with the parameter we compute for each of them. And you can see already that they're very different. And we're going to see throughout the course that, in fact, is the case. I'm not going to go a lot into the studies. I'm going to let you read the notes. Here's what I'm going to say about studies. So I kind of lied a little bit at the beginning. I said we use statistics to make decisions using data. And that's generally true, but not always. So for example, when you're doing a study in real life, collecting data is very time consuming and it's very expensive. And one of the things that you find out when you begin to start a study is that you're making errors. You'll realize there are things that you weren't aware of. So very often what people do initially is they do something called a pilot study, just to see whether or not they can collect the data reliably, what sort of result they're getting and stuff like that. And there's a whole lot of issues that we'll talk about down the road. But they're kind of doing a little pilot study to see how things are going to turn out. Once they do the pilot study, then they go to an actual statistical study. And when we're doing a statistical study, there are 2 types of studies. On the one hand, you have an observational study. One of the things I love about statistics is that things sound like what they are. It's a study where the researcher is just observing. He's just watching and writing down stuff and not doing anything, okay, other than just observing. And there are a lot of different types of observational studies, okay? So the book goes into this. I'm not going to go into this a great deal. One of the things that observational studies are weak in, though, is establishing causal relationships. In other words, cause and effect relationships. So, for example, I might observe that people who smoke a great deal have a higher incidence of lung cancer. Can I conclude from that that smoking causes lung cancer? Well, we're gonna talk about that in a second. It turns out the answer is no. One thing to realize, and some people have this misconception, that you cannot determine cause and effect relationships from observational studies, and that's not actually true. A more precise statement is that you cannot determine cause and effect relationships. You can't prove them using only observational studies. So for example, how do we know that smoking causes lung cancer? And this is something that's now been very well established, it's accepted. How do we know that? We can't do experiments with people, right? We can't say, okay, you smoke and you don't smoke. That's unethical. So it was done using observational studies, but there was more to it. And if you're interested, you can read something called the Hill criterion that was developed by Bradley Hill back in the 1950s. And there's other variations of that that actually talk about how you determine cause and effect relationships. But it's a fascinating area. We're going to be interested more sometimes in what we call experimental studies. And those are the studies where we're actually going to determine cause and effect relationships. So the idea is that the researcher now manipulates some part. He either applies a treatment or he controls some factor or environment or whatever on the subjects. And that's called an experimental study, where now the researcher is tweaking the knobs and manipulating things and intervening. So drug trials, for example, are a classic case of experimental trials. What we generally have, and this is what I outline in the notes, when we have experimental trials, we usually have a control group and an experimental group. In other words, we have an experimental group, that's the group that we're going to apply the treatment to. So for example, if I say, oh, I have this great new drug that's going to increase your IQ, I'd split my subjects up and I would give half of them the actual drug, the treatment, and I would give the other half, well, what would I give them? I would give them nothing? Well, I could, but what we generally do is we give them what's called a placebo, something that looks like the treatment, but it has an inactive ingredient, what they call a sugar pill. Why do we do that? Well, because, well, you know what? No one actually knows. No one understands the placebo effect. What we do know is that when people think they're getting a treatment, they will sometimes respond favorably, even if the treatment doesn't have anything in it. But the placebo effect is one of those great mysteries. It turns out the placebo effect works with dogs, right? Very strange. The color of the pill has an effect on how effective the placebo effect is. It's a very sort of weird, mysterious thing. And it's a very important thing to recognize as a student, because the lesson that you learn from the placebo effect is that there can always be things out there that we're not aware of. It's always good to be kind of humble and realize that there may be things that we just don't know about. And the placebo effect is a classic example. Now, there are some principles in how we conduct an experimental study. So the one is called randomization. There are a couple of basic principles. Randomization means that we randomly choose who is going to go into the control study, the control group and the experimental group. So here are all of our subjects for our study. And in randomization, we're going to have these two groups, our control and our experimental group. And so we maybe have, we'll make it 6 people, okay? And the idea is that we're going to randomly choose who goes in what group. Why do we do that? Well, because we don't want to introduce any bias on our own part. And you might say, oh, that's stupid. I could do this in an unbiased way. And the answer is people fail a great deal at doing this. I'll tell you a really quick story. There was a very famous statistician at Yale. His name was Sneckdor. He was doing this experiment, and he was testing to see whether or not a certain type of food increased the weight of the rats. And it was known from other studies and these pilot studies, okay, that it appeared that this food was very, very effective at increasing the weight of rats. Now, why You would want big rats. I don't know. I don't know what the application was. This is just the story that I know, okay? But here's what happened. He did the experiment in the lab with the students, and they didn't see any difference. They had this control group where they were feeding them kind of like, just average quality food. This experimental group where they're getting this great food that's supposed to add weight, and they're not seeing a big difference. And he was puzzled. And one of his students said to him, Professor, I seem to notice that when you were picking out the rats, notice that he did it. He didn't do it randomly. He said, I noticed that when you were picking out the rats, you seemed to put the thinner rats in the experimental group. And he thought about it, and he said, you know what, you're right. He said, I really wasn't conscious of it, but I felt bad for the thin rats. So I wanted them to get bigger, so I put them in this group. And this is a professional statistician, okay? A guy, it's a very famous statistician. That's why we don't trust ourselves, all right? We generally let a computer do it. The computer will randomly pick this. So the first thing is randomization. So maybe we give people numbers 1 through 6, right? And the computer randomly draws one, okay? So maybe the computer draws 3, and that first person goes to the control group. And then the computer draws 2. That person goes to the experimental group, right? Draws 1, goes to the control group. Draws 4, goes to the experimental group. Draws 6, goes to the control group. 5 goes to the experimental group. All right? And that's called randomization. There is a variation on randomization that people sometimes use called block randomization. And what that means is when you have another factor that you already know a priori is going to affect your results, you tend to break up your sample into blocks and you randomly choose from each block. So let me give you an example. Gender. Very often certain drugs, the way they're metabolized, are actually highly dependent on gender. Okay, so what you would do in a block randomization is you would start off with your subjects and you would already have them in blocks. So these would be females and these would be males. Okay, maybe you have 4 females. You usually like the design to be balanced, meaning you have the same number in each block, okay? And then what am I going to do? Well, the same principle applies, right? I'm going to have my control group, I'm going to have my experimental group, and I'm going to randomly choose females and put them in the control and experimental the same way I did previously with just a randomized design, okay? And then do the same for males. So maybe these 2 females are randomly chosen, they go to the control, these 2 go to the experimental, and the same thing for the males. And that's another thing that people do sometimes. Last thing I want to talk about, I'm just going to refer you to your handouts, is the type of things we can do, okay? So when we have one variable, and we're going to concentrate in the beginning of this course primarily on one variable, what can we do? Well, with that variable, we're going to be looking at the value of its parameter, right? So, for example, when the elections come up, what is the parameter everyone's interested in? What percentage of all the voters are going to be in favor of a certain candidate? That's the parameter, right? What can you do with parameters? Well, first of all, you can detect if a change occurred. In fact, that the COVID-19 example I just gave in Florida, I'd be detecting to see if a change occurred, right? Did the percentage of positive test rates change from 4.2% to a higher value after phase 2 was initiated? Okay, so the first thing we can do with one variable is we can see if some sort of change occurred in the population, which is reflected by the change in the population parameters value. Sometimes we have no idea what the parameter value is to even detect a change. So for example, what percentage of people in Morocco have cell phones? I have no clue. Yeah, I could probably take a decent guess, but I have no idea. What would we do? Well, we'd estimate. So the second thing we can do is we can estimate a parameter. And when we do that, we put a little error bar around that estimate, and we call that a confidence interval. And we're going to talk about that. You hear confidence intervals every single day on the news now. What percentage people are going to vote for Biden, right? So it's 42% plus or minus, that little error bar, right? And that 42% comes from the sample, and that 2% error bar says that we think the true value, the parameter value, lies within 2% of 42%, or we think it's between 40 and 44%. That's what we can do with one variable. For two variables, we can look at how they're related. And unfortunately, in this class, we're not going to get to do much with two variables. The only thing we're going to do with two variables is we're going to look at the case where one is categorical and one is quantitative, okay? And so there's going to be two different types of scenarios we look at. The one is called an unpaired test, where we're looking to see if the parameter value between two populations is different. So I could have females and I could have males. And this is called an unpaired test. And what I want to see is I want to see if the parameter value for the females is different than the males. So I could ask, for example, are males taller than females? Notice that question in and of itself doesn't make any sense, right? I mean, you could take me and then take a person from the women's volleyball team, and they're probably going to be taller than I am. On the other hand, they could take you, if you're a female, and they could take a member from the NBA, right? And they're probably going to be taller than you are. So on an individual basis, it doesn't make sense. But we can look collectively, right, at the whole population by looking at the value of the parameter. So we can ask, is the average height of all the females less than the average height of all the males? And this is called an unpaired test, okay? Meaning that these two don't have anything in common with each other. On the other hand, you can do something called a paired test, where you're looking at the same individual and you're making two measurements, okay, on them. And so the example I give in the notes is, you could ask the question, do Embry-Riddle students perform better in the morning or in the afternoon? So what would I do? Well, I might take a bunch of people. Let's say I'm going to have 3 people, way too small a sample size, but that's okay, just for the sake of, illustration. So Alice, Bob, and Carly, right? And maybe I could do some sort of cognitive test in the morning and a cognitive test in the afternoon, right? Maybe measure their IQ. So maybe Alice is, 120 in the morning and 118 in the afternoon. And Bob's not quite as swift, right? So maybe he's 98 in the morning and 101 in the afternoon. And Carly's maybe, 110 and 112. Same individual, I'm making 2 different measurements. Very often when people do drug trials, they do paired tests, right? They'll measure your blood pressure before you're given a hypertensive drug and then afterwards and stuff like that. So there's many different ways that paired tests can manifest. But the idea is you're looking at the same thing and you're making multiple measurements. Okay, last issue is statistical pitfalls, and I'm just going to go through the sheet. Biggest problem when you're doing surveys is the fact that generally surveys are very often self-selected. What that means is the person gets to decide whether or not they want to respond. That's a big problem. And that's one of the reasons why you almost cannot trust the majority of polls you hear on the news if they're taken by that company where they have call-in sort of polls, right? So call in and tell us, do you think that, Trump is the Antichrist or whatever, right? They have these sorts of call-in survey polls. You just simply cannot trust them. And the reason why is they have 2 different types of biases. First, you have what's called response bias. In other words, the people that feel really strongly, right, who either really love Trump or really hate Trump are going to call in. But they really represent, to some degree, kind of the fringes of the political spectrum, right? Meanwhile, you have like the middle 50 or 60% in here, and from them you end up getting what they call non-response bias. In other words, you're sampling less from the majority of people, you're not hearing from them at all. So the sample that you're getting is really a gamish of highly polarized views where you've left out the majority of the population. That's hardly a good sample. That's what's going on. The book gives several examples of how the questions that you ask, the order that you ask, whether or not they're leading questions, These are all issues, okay? And there are a gazillion other issues with surveys. So there are tons of different things with surveys that can affect it. The people asking the survey can have a very big, effect on the outcome also. And I won't bother to go in those, but those are things that if you actually conduct surveys, you really have to study and make sure that you understand, because they can really mess up your survey easily. When we're talking about relationships, so we said that when we're looking at two variables, we have relationships. And a relationship really means that two things tend to go together, okay? So for example, higher temperatures tend to go with more exposure to sunlight, okay, something like that. One of the problems that people make is they think that because two things go together, they're either correlated or associated, that it means there's a causal relationship. And so very often you hear people say things like correlation does not imply causation. Just because two things go together doesn't mean one thing causes the other. A classic example, and it's a really good example, it's in the book, is ice cream sales and drowning. So as the amount of ice cream sold goes up, the number of drownings go up. But nobody thinks that ice cream sales is causing drownings or that drownings are causing increased ice cream sales. Neither one of those scenarios make any sense. What's really going on is there's a third variable called a confounding variable, or sometimes called a lurking variable, that's actually causing both of those. And in the case of ice cream sales and drowning, that lurking variable is temperature. As the temperature goes up, it causes both ice cream sales to go up, and it also causes the number of drownings to go up because more people are out swimming. So these sorts of things occur a great deal. There's actually an entire website devoted to what's called spurious correlations. It's hilarious if you ever want to read it, okay? Now, going back to the thing about lung cancer and smoking, okay? Yes, they are correlated. But again, that piece of evidence alone does not prove that smoking causes lung cancer. So it actually took a lot more than that. And again, there's a whole list of criterion, and you can read about it. There's one example of what they call Hill's criteria that tells you all the different things two things have to meet in order to be considered to be causally related. So there has to be a temporal association. In other words, you can't get the condition before the treatment occurs. There also has to be intensities that scale. So as you smoke more, the percentage of lung cancer should go up and stuff like this. And so there has to be a number of different criteria it satisfies. Sampling issues are a huge deal. So we have to make sure that our sample is large enough, that it's randomly chosen. We won't get into those issues, but those are things that can have a very, very big effect, okay? And that's a lot of what happened. Actually, I'll tell you this very quickly. In the 2016 election, the American Statistical Association commissioned a post-mortem analysis, so to speak, of what happened. Why did all of these major polling companies get the 2016 presidential election prediction so wrong? And even the exit polls got it wrong. And it had a lot to do with sampling issues and surveying issues. And the bottom line is nobody actually knows to this day exactly what it was. It's a fascinating issue. The last one is what we call practical versus statistical significance. And this is important, so I'm going to write this out. So you can have a difference that is statistically significant. So for example, suppose I claim I have a drug that increases the percentage that you're going to have a male baby. So I give my drug to 1,000 people, and I find out that there are, we'll say, 550 male babies and 450 female babies. Okay. Let me make it a little less dramatic. 520 and 480. Okay. Now, when you do this analysis, what you'll find out is that that is actually statistically significant. In other words, the probability that this could have happened by random chance is pretty low, believe it or not, because we have a really large sample size. So one of the things that happens is if we have 1,000 babies, on average it's going to be 50-50, 500 and 500. We know there's going to be variation. Right? The question is, when is that variation so large that it can't happen by random chance, or it's too unlikely? And so the criteria for statistical significance is when an event only has a 5% chance of occurring or less. So when there is less than a 5% chance we could get our observed observation. I'm sorry, our observed results. Then we say it's statistically significant. It couldn't have happened by random chance because it's too unlikely, so there's something going on. Let me go back and change this a little bit. I'll make this 450 and 550 and 450, okay? Because I know for a fact that that's statistically significant. And we're going to do this calculation later on. We're going to find out that just by random chance, it's unlikely we could get 550 male babies, all right? Okay, so this result is statistically significant. Is it practically significant? Well, you know, this result seems to suggest that it increases the percentage by 5%, right? So instead of a 50% chance you're going to have a boy, now it's a 55% chance. Well, that isn't all that great. So we'd say that it's not practically significant. So there's a big difference between the two. Statistically significant means it couldn't have happened by random chance, that there really is something going on. But in the case of it being practically insignificant, we basically say, yeah, you know, this couldn't happen by random chance, but in reality, you know, this difference is really not practically significant. And that's the idea behind those two. And we'll get into this a lot more. This will form a better portion of our class. All right, thanks for watching, and I hope you enjoyed it. If you have any questions, feel free to post them in the comments below. Or, of course, you can always contact me. All right, thank you.